Okay, welcome to the panel on the best architectures for solid-state storage arrays. Just some quick introductions before we dive into it. So my name is Nigel Poulton and I'm a bit of a storage head. The potential disruptive nature of solid-state storage keeps me awake at night. And if that's not sad enough, I also run a technical website and a technical podcast in my free time. So that's enough about me. Let's introduce the panel. So starting at the end, Tom, can we just keep it brief, about 30 seconds each?
Sure. So my name is Thomas Isakovich. I'm the CEO and founder with Nimbus Data Systems. And we are a developer of multi-protocol, all-flash network storage systems.
Okay, my name is Umesh Maheshwari. I'm the CTO and founder at Nimble Storage. We build storage systems that combine capacity, performance, data protection, all at low cost.
So I'm Jonathan Goldick. I'm the software CTO at Violin Memory, and we make an all-flash enterprise class array to take on all tier 1 applications.
And I'm Dave Wright. I'm the founder and CEO of SolidFire. SolidFire is building a scale-out, all-solid-state storage system for large cloud computing environments.
Okay, thank you. So the intent of this panel is to talk about the best way to design a solid-state based storage array and hopefully talk about some of the thinking and some of the theory behind that. To introduce it, there will be zero talk about 20-year-old architectures. There'll be no mentioning of config locks and bin files. I think we promised not to talk about 10-bay storage arrays with thousands of disks that take up far too many floor tiles, suck enough power to power or enough energy to power a small country, and belt out enough heat to melt the polar ice caps. We won't talk anything about hypers, metas, striping, or concatenating, and we will definitely not mention any rules of 17. Instead, I think we'll talk about some architectures that are designed to meet today's I/O requirements and hopefully tomorrow's. I think to start the ball rolling, question number one, there are almost certainly people in the audience today, customers and also some vendors, who think that you guys are probably a bit crazy and maybe have your heads up your rear end in some respect. Sticking solid-state storage at the end of either a fiber channel cable or a copper cable, or in some instance at the end of a cloud or a public cloud connection. Surely by doing that we're hamstringing the capabilities of solid-state. So let's start the ball rolling by taking your opinions on that, and please don't hold back.
Well, if you don't mind, I'll just get that started. I think if you look at what led to the adoption of SAN and NAS infrastructure, performance was certainly a criteria, but it wasn't the driving criteria. The driving criteria was manageability and scalability. And if you look at virtualization, the driver is not performance. The driver is maximizing utilization, simplifying manageability. So I think from a sheer physics perspective, it's absolutely true that anytime you've got to go traverse some speed of light distance out of a server onto a network, you're going to face some sort of performance impact. But I think for the broad use case of storage, and particularly shared storage, that delta is more than acceptable. Because the customer today is coming from 15 or 20 milliseconds. And if you're going to take them down to 400 microseconds or 200 microseconds and then get into an argument about how it could be another 50 microseconds if it was PCIe, you can certainly have that argument, but that's an argument that has not won. If that was the argument that won, we would never have SAN, we would never have NAS, we would never have server virtualization, we would never have desktop virtualization. So it's not that the two technologies are not complementary or competitive. You'll have PCIe flash, you'll have network flash, but the thought that you're wasting flash on the end of a line, I think misses the big picture.
I agree with Tom completely here that putting flash in network storage is not hamstringing it at all. For the vast majority of applications, it does not matter whether you are losing 100 microseconds, which is what it takes to do a network round trip. What matters is whether you are getting down from 10 milliseconds, which is what you get from disk, down to a few hundred microseconds. right? So unless you're looking at applications that are ultra latency sensitive, like maybe trading applications or which require a lot of throughput, data analytics or warehousing, it does not hurt at all.
So I can't agree with any of that. And who buys Flash and says, I don't care about performance? Okay? I'm not saying every app requires ultra low latency, but you just listed two of the largest apps in the world that do. Either people who monetize microseconds or people who are paying vast fortunes to use a new undersea cable for latency. Latency is a big part of what Flash delivers. To say, we strongly believe, look, network attach is important, but so is PCIe attach. That's why we do both. Fiber channel is a big part of the market. So is iSCSI. But there are people who think InfiniBand is the best thing to use. They shouldn't have to make, a fundamental decision that if I want PCIe, it has to be in the server. Some people actually want PCIe outside the server. They want all the advantages of a network-attached array, all the manageability, but they don't want to give up the latency. I don't know why you'd have to make that decision. Fundamentally, our customers don't.
So I'm going to look at this a little bit differently. And first of all, I think one point of clarification, although we sell our systems to large cloud environments, they're not designed to be accessed across the WAN. They're designed to be accessed by cloud computing resources that are in the same data centers as the storage we're selling. So we're still dealing with Ethernet and local area network type latencies. When we look at Flash, we see more than just high performance, high IOPS, low latency. What we really see as one of the biggest values of it that we really take advantage of is the ability to give consistent performance across a wide array of applications in a shared environment. Typically in a disk environment, even if you could get one good performance for one application, once you put a bunch of applications on that and you got the heads flying all over the place, your application performance is going to be horrible. One of the nice things about Flash is that it gives very consistent performance across many applications that are sharing that performance. From the perspective of an individual application, a couple hundred microseconds of latency, whether it's from the Flash or whether it's from the network, isn't the end of the world. What they want to see is consistent performance. They don't want to see 1 millisecond one day, 10 milliseconds the next day, 30 milliseconds the next day, 20 milliseconds the next day. Flash in the appropriate architecture is very good at delivering consistent performance to lots of applications at the same time, even if individual applications don't require exceptional performance. And for those applications, Flash in a PCI form factor is probably still the right way to go. But for the vast majority of applications, just having very good, consistent performance is far more important.
Any other comments from the panel?
Well, I think we can see this parallel in server virtualization. There are a large number of customers that remain bare metal, unvirtualized, and they're going to stay that way until the end. And to them, that 5% or 10% performance impact of the hypervisor is unacceptable. And I think Jonathan's right. In trading applications and others, that is the case. But I would agree with David's comment that the bulk of the industry, and what I said earlier, I think a good 90% plus of the storage infrastructure that's out there would trade 50 microseconds for all the manageability, usability, efficiency of a shared infrastructure.
My point is they don't have to.
Well, if you're on the other end of a fiber channel wire, and so am I, you've got the same speed of light problem that anyone else does. But if you're on the other end of an InfiniBand wire, so do we.
But if I let them do fiber channel or PCIe, then they have both options.
Sure, and you can do InfiniBand too. And we can do InfiniBand and fiber channel as well. So it just depends on which side of the network you want to be on. So, so I would agree with you that from a PCIe perspective, yes, but PCIe isn't shareable. Okay, so you can't compare apples and oranges. PCIe.
Actually, come to our lab. I'll show you 4 systems using it. It can be. You can connect multiple servers through PCIe to one system.
If you can share a common LUN and you attach a clustered file system and have all that intelligence in your box to do it, and are you shipping it?
Oh, I just put I put 4 servers each with one LUN. Why not?
Okay. Well, I would like to see it because
Okay.
the current marketing your product is one server to one piece of storage.
We're talking about technology,
Exactly.
not products.
Okay.
Yes.
So I would like
Really?
to make.
Okay.
So thinking that the network slows down your access speed for most applications is like thinking that the speed limit on the highway determines your commute time. right? That 65 miles per hour speed limit. For most cases, it does not matter. It's all the traffic lights and the queuing that happens in between that determines your commute time. So that's my take. Yeah, it's the network speed. Networks are fast. They do not come that much in the way. It's
I think,
somewhat
well, second, we have 80% of our, 80% of people, I still have fiber channel, absolutely. But there are use cases where you want alternatives.
Okay, guys, any questions from the audience? Okay, next question then. Using solid state in a storage array, what is the best way to do that? Is it best used as a cache extension, like a level 2 cache within the array, as a landing spot for the hottest parts of a lung, or should we just throw solid state at every part of a lung? And this is within the context of a storage array.
yeah.
Oh, okay. Go ahead, Umesh.
Okay. All right. So, well, there are two parts to this question, I believe. One is, before we talk about caching versus tiering, is a bigger question of all flash versus hybrid.
Yeah.
Right. And the truth there is that most applications need both performance and capacity. You cannot say these applications care about performance, these about capacity. So I can get into numbers here, which I would like to at some point. And just as it's not good to have too much capacity without enough performance, which is the problem with hard disks, it's also not good. It does not help to have too much performance without capacity, right? And there, that's the thing that pushes one towards hybrid storage, because the cost of capacity, which is a necessary part of this equation.
Is it fair to say then, if or when solid-state devices increase in capacity, that argument will go away, or do you not see that happening?
Well, as so data storage needs will also increase, and it's possible, and in fact, it's a given that at some point solid-state technology will replace spinning media, no doubt about that.
Cool.
But when that will happen and whether flash is the chosen medium for that replacement is not clear. What is clear to me is that just as today we can think of using flash as cache for disk, it might be that flash is the disk layer, the endpoint of storage later, and there is some other technology that would act as a cache. So the thing about having a large enough cache within a storage system would still make sense, even if flash replaces disk.
Okay, any other thoughts?
So, yeah, I was going to say, Umesh touched on the idea of the ratio of capacity and performance. What is the right ratio of capacity and performance? Because ultimately, that's what people care about at the end of the day. They don't want to be wasting a ton of capacity. They don't want to be wasting a ton of performance. And so that ratio is really what matters here. And the problem today is that you've got disk on one end that has a very high amount of capacity and a very low amount of performance, and you've got flash on the other end, which often has a very high amount of performance but a very low amount of capacity. And one way to deal with that delta and deal with the reality of the fact that most applications fall somewhere in that middle part, not really completely on one end or the other, is to try to cache or tier in the storage array and try to shuffle the right data to the right media. Another approach to that is to build a storage system that has flexibility, even with flash, to have a balance of capacity and performance, and to allocate performance to volumes that need it and away from volumes that don't, while still allowing the volumes that don't need it to use capacity. And it's this concept we call performance virtualization that allows you to steer the performance in a collection of data and a collection of applications to applications that need it, and steer capacity to the applications that need that capacity. And having a flexibility in an architecture, since we're talking about storage architectures, to use different capacity and different performance flash devices to obtain the right overall balance of capacity and performance you need. So if you need more capacity, great, use larger, cheaper flash devices that have less performance. If you need more performance, use higher end, more expensive flash devices that have more IOPS but less relative capacity. And those options exist in the marketplace today. There's actually a much broader range of performance options than just one thing we call flash. And using those different technologies in a storage array to obtain the right aggregate amount of capacity, the right aggregate amount of performance, and then having a storage architecture that can deliver capacity where it's needed and performance where it's needed, we think is the better way to do it.
Does anybody else have any quick comments? Because we've got a couple of other questions.
I would say I agree with Dave. A lot of what people are looking for from Flash, though, is predictable high performance, and not just IOPS, but latency. And the problem about caching systems is, by definition, you're trying to predict the future from the past. And any time an application restarts or something changes, caching falls apart. Or you move the model where everything is actually Flash resident and disk resident, so all reads come out of Flash.
Sure.
But another big focus is you got to also support writes. I mean, you can't. Caching is we had this last panel discussion for people who haven't seen it. You should. Caching is not just reading. I've got to actually be able to write data. And fundamentally, what people pay for, the reason why they're paying a premium for Flash is for predictable latency, predictable performance. If it spikes all over the place, if I can only, if I use 50% of the performance, available in the system, and now I'm spiking to 5 milliseconds or 10 milliseconds, I might as well be using spinning disk.
Cool. Tom, real quick.
One final comment. I think part of it is just determining the proper placement if there's going to be both Flash and disk. I think all of us probably agree there's going to be a little bit of both. The question, though, is does it all belong necessarily in the same box? And there was a comment made earlier today on one of the panels about how tiering and the intelligence is actually moving closer to the application layer as opposed to being resident in the storage system. And I tend to agree with that. If you look at the latest versions of, for example, VMware vSphere with storage DRS capability, you're seeing now the hypervisor actually incorporating some intelligence to migrate data and place data depending on the underlying performance of the system. And the reason that's a bonus to customers is that they don't need to buy into a Swiss Army knife storage appliance where they're going to probably end up overpaying for all the different tiers. They'll overpay for the SSD, they'll overpay for the mid-range disk, they'll overpay for the SATA disk. Instead, they can get a cost-effective SATA solution, a cost-effective Flash solution, let the intelligent data placement happen at the app layer or the hypervisor layer and accomplish it that way. In my view, that's where this is headed. And if that's where this is headed, then the hybrid solutions, in my view, are really relegated to, I think, a fairly entry-level customer set that doesn't want to deal with two boxes. But most organizations that are virtualized will see the cost advantage of actually having best-in-class Flash systems and best-in-class nearline systems being independent units.
Okay, I need to move it on. A topic that's come up throughout this symposium this morning has been the implementation of inline, non-disruptive deduplication and compression without impacting performance on a solid-state array or on a solid-state device. How is that possible? There's been a lively discussion online about this. Is that accomplished through FPGAs, through ASICs, through GPUs? How is that done? How can you make it non-disruptive?
Well, for one, I also have the same very thought and question in my mind because none of the vendors that do full-time deduplication have a capability of turning it off. So how would you ever know that it was performance neutral deduplication? I think that's
very good point.
Thank you. I think that's.
Hey, I gotta be nice to him sometime.
I think that's.
Dave has something to say.
But if you just don't mind, I'll just finish my thought. I think though, either way, dedupe is going to work its way into the infrastructure. I'm a big believer in the technology.
But you don't think it can be done non-disruptively inline without impeding performance?
I think if people, I suppose in time, we'll talk technology now as Howard would like to, with GPUs, with FPGAs, with custom hardware, maybe with just lots of brute force processors, maybe you can get to a point where you minimize it. But I think even if you ask customers, can you do non-disruptive real-time encryption on data in flight to a storage array? The answer is consistently no.
Yeah.
And dedupe, in some respects, is not that different. Now, dedupe has other benefits. It can actually help accelerate performance in some cases, and maybe that can sort of offset the performance negatives. But there are going to be applications that don't benefit tremendously from dedupe, and I think it's of value to those application users to give them the option to move the dedupe off to the side, use their storage in a non-dedupe mode, get the minimum latency possible when they care about it for the performance people that are really minded around that, and then turn on dedupe for the applications that can benefit from it, such as fully provisioned VDI installations and things of that nature.
Okay, I know, Umesh, you wanted to comment previously, so let me give you the mic now for this question, because you guys do inline compression, right?
That's right. So we do inline compression on both flash and disk. and our architecture is such that we can do this sort of natively in a simple manner. We don't do dedupe yet. Dedupe is easier to do on flash than it is on disk because you can do certain things with random reads on flash much better than you can on disk. But I would say one thing, that the benefit of dedupe in primary storage is somewhat limited. It does not quite nullify the cost multiplier that you're paying with flash. So, compression you get around 2x, and you can do that with both disk and flash. Dedupe you get in primary storage, I would say about 2 to 3x is the max. And I was at Data Domain, so I know what the numbers are roughly.
But Umesh, what I really want to know is, how do you compress inline without killing performance?
So that is not so much about compute anymore. It used to be that people would talk about, how many megabytes per second you can compress on a core. Now you have plenty of cores. You can do that easily. It's not about compute. It's about how you store the blocks on disk or flash, because after compression, they are variable size. And how do you fit these variable size blocks within fixed size slots that you might have in the disk space or in the flash space? So that's where one needs to think of a completely different layout so that you can take these variable size blocks and concatenate them together and write them into large size allocation units, and that's what enables it.
Okay.
For the dedupe front, quickly, what you need again is not so much compute. You do need that, but it's also access to index. The Pramabit talk made that very clear. It's finally you need to access an index to figure out whether the blocks are duplicate or not, and that index is so large it does not generally fit in memory. And how do you access that? How do you minimize the amount of I/O that you need to do
Great.
dedupe?
Thank you.
So as someone that does compression and deduplication in inline as part of the storage system with very minimal performance impact, I think it's important to explain why it's perceived as hard and then why we're able to do it. So there is definitely a cost to doing compression and deduplication. The actual compression algorithms, the hashing algorithms, the table lookups that you need to do, the metadata lookups that we've talked about, there is a cost there. And that's one of the reasons that in a traditional storage array architecture, it's very difficult to do these, particularly with flash, because you've got a controller and then you potentially have hundreds of disks that it's trying to process I/O for. And if you're doing that, you don't have much time to process each I/O, because you've got a lot of I/Os going through a single controller, a single bottleneck, and it doesn't have that much processing power or that much memory. Typically, you've got something like one core for 100 disks. And when those were spinning disks, you could actually do a lot in the 10 milliseconds or 5 milliseconds that you had for an I/O. When each I/O is 100 microseconds, you can't do much across that wide range of disks. So to address that, we've adopted a scale-out architecture. And since we're talking about architectures, we think ultimately the best architecture for large-scale flash deployment is a scale-out architecture. And a scale-out architecture means that you deploy individual nodes that have CPU, memory, network, and flash storage in them. And as you grow, you add more of each of those elements. And what it means is that we have a much higher ratio of CPU and memory to each individual flash drive that's in that box. So rather than one core to 100 drives, we have something like one core to one drive. And so we have a tremendously larger amount of processing power and memory that can be devoted to processing that data as it's coming in or coming out, doing compression and deduplication in real time, using other things like NVRAM to hide some of the latency that's involved in these processes, and ultimately give you something that is scalable. So as you're adding capacity, you are able to continue to compress and deduplicate all of that data, and you're not just adding disks and making that controller a bigger and bigger bottleneck.
Any thoughts from Violin memory?
So we look at dedupe as something that we want to do asynchronously to keep it out of the latency path. There's nothing that says it can't be in the latency path once the technology gets there. I mean, we're obviously a big fan of hardware acceleration to make these things work. The things that worry me most about when I look at a system, since we tend to focus on performance under failure, is if I have an n-way controller, and even if n is only 2, we do symmetric access. We want every port on every controller to be able to reach any byte. So if one guy is deduping, and so the whole point of promise of dedupe is maybe 80% of the writes disappear. But all that means is 80% of the time I'm changing a pointer to point to another block. Well, if I do that on one controller, I've got to tell the other controller that I did it. Because if he gets a read on that block that I've deduped, he's got to go to the right place. So I've got to tell one controller's got to tell the other one.
Struggle.
It's exactly. It's like, wait a minute. I'd like that controller that what I'm limited by in dedupe is actually not the dedupe engine. It's not the DRAM. The permabit guys really do deliver what they say they do. I've got to tell one controller to the fault tolerant one, even if there's only one other one, much less a scale out, that I did it. And that's going over some bus, a PCIe, some network, something. Every write. So 80% of the time, I've got to tell somebody else I did something. And what happens if I crashed in the middle, or I had a network partition, or anything? Async is reliable. You know the performance won't change. It works to n-way in controllers, all of that. So that's why I try to focus on the async. It's not like I don't like inline. I understand the advantages for Flash in terms of endurance. But I always look at what happens when things go wrong.
Any comments from the audience?
Oh, lots.
That's a no. Okay, next question then.
Let's go.
Oh,
So,
I don't count
for most end users, it's the good enough threshold, all right? So what they will say is basically that he has a balanced architecture, right? So I got enough compute power, right? One inline to do the compression, not see a significant slowdown. So if somebody's going to say, hey, that performance is great for me, and I'm also getting the inline to do the compression, their system is going to look a lot more interesting, right? To a certain degree, but
and I was going to say, it goes back to the question of what you're optimizing for, right? If you are optimizing for the absolute highest level of performance, the absolute lowest latency, if you're going to put that thing on the PCI bus, you're not going to want anything touching that data on its way in or out of the flash. And so, yeah, things like compression and deduplication are going to be much harder to do in that. If you're looking for a balanced architecture that gives you the right balance of capacity and performance, and you can get to a better balance using data reduction, and can do so with a very minimal impact or even a performance benefit in some cases from data reduction, because you can reduce the amount of data you have to store on the actual drives, then that makes sense. So there are always trade-offs there, but we think that those technologies across the vast majority of data make a lot of sense.
So I'm sorry, to be fair, you'd say it's mid-range versus high-end. Is that how you
No, because we scale down to 5 terabytes, and we go all the way. We have a spectrum of products. The reality is that customers don't care how you do dedupe, as long as they care about the performance impact that they paid for, and they want this. They want to pay a certain price per usable byte.
and it sounds
Gigabyte.
like tier 0 performance versus tier 1 rather than
but even
mid-range versus...
no, it doesn't, because tier 1. We think of ourselves as tier 1, not tier 0. I don't even know what tier 0 is. Sort of this new category that the disk vendors are creating to.
Tier 1 versus tier 2 then.
Yeah, but what I look at it is, if I tell you I'm deduping and he's deduping, and as long as I say we're doing it in a realistic and high performance way, he guarantees a certain performance level, we guarantee a different one. That's what people care about. It's not the async versus sync they care about. It's the compression that they get at the end of the game.
Okay, great.
Hey,
Quick.
Nigel, I have a question.
Okay.
So my question is for Dave. You talk about using the scale-out architecture and then, doing the inline duplication for all the workloads. We all understand that not all the use cases would benefit in the same fashion. Different use cases and different workloads are different. What's the downside in providing it on an on-demand basis or on a workload basis? Why do it inline for every workload?
Yeah, that's a good question. So the question, for those that couldn't hear it, is some workloads benefit from deduplication more than others. Why not provide it as an option on a per volume or per application basis as to whether you deduplicate or not? And for us, fundamentally, it's because our architecture, our data placement technology, everything about what we've done, about how we place data in the array, is based on a content addressing architecture that has as just a natural attribute of it, the deduplication. So we can't just decide to turn off deduplication for an individual volume per se, because we would need to figure out some completely different way to store that data. That would be different than how we store the data from all the rest of the system. We don't use a pointer-based indirection scheme like a lot of storage systems that deduplication. We use a native content addressable and content-based placement scheme for all of the data in our scale-out system. And so because of that, we actually get deduplication as a native property of how we store the data. It's not additional process or additional work that we do to do that.
Thank you. Final question from the audience.
Yeah, I want to challenge Jonathan a bit on customers not caring about inline versus async dedupe. The problem with async dedupe is that you might end up with a workload that consumes all of your space, and then 6 hours later it frees back up.
If it was 6 hours, I would totally agree with that.
Much more predictability about.
Oh, if it was 6 hours, I totally agree with that. What I mean is immediate async.
So not overnight.
So I mean immediately in the background is, look, I do a write, I want that write to be fast. And I want guaranteed predictable latency on the write. I want dedupe to happen almost as close to immediate as I can without sacrificing user performance. Yeah, I wouldn't, nightly dedupes, I'm not looking at that.
Async as opposed to post-process?
Yeah, it's immediate async is basically post-processing, but I do it immediately. I'd like to do it as soon as it's still in the cache.
Which obviously falls down when you're under high stress, which is the time you might.
It depends on the level of performance that you've got available to you. I mean, remember, we're doing writes, what we've done, we've sized the system, we're at the maximum write IOPS, at the maximum sustained, we can do this. We have plenty of available CPU resources and DRAM to do this.
So dedupe doesn't fall behind when you're under your maximum write load?
No.
So how does the end user see that different from synchronous?
Because their writes are acknowledged because we're writing through to this flash immediately, so they don't see a latency hit.
But you have to potentially write the data even though you're not going to use that write eventually. So that's why it's asynchronous, as opposed to an inline mechanism that can discard the data before it hits the flash.
And by the way, there's nothing that prevents us from doing inline. Just like I said, I think it has bad failure characteristics when you have multiple controllers. I'm just talking about in general architecture. I think that's a failure of these systems.
So I want to move it on actually to one final question. It's going to have to be quick, guys, but I think it's important architecturally speaking. Build it yourself or pick it from the shelf. So, design it and build it and do it all custom in the face of the industry trend to commoditize. What is the best way to do it?
Well, I'm a big believer that to take full advantage of the performance, density, and power saving potential of Flash, you have to build the system architecture, the sheet metal, the skin, the controllers around the silicon.
Okay. Umesh?
Yeah, I agree with that, and we have built a file system that
I'm thinking more
leverages-
about hardware,
Yeah,
ASICs, flash chips.
I see. Okay. Again, I don't think that the hardware makes that much of a difference. And the reason again is that people talk about putting flash in a disk form factor across HBA. All of these latencies really compared to the latency of network storage access and disk access, the deltas don't matter that much. So unless you are building a cutthroat performance device, it does not matter so much.
I have to disagree.
Yeah, I got.
I mean, because we just started an argument at the beginning about this about PCIe versus external arguing over 50 microseconds. So now we're saying we can stick SSDs behind a SAS expander that's going to throttle your bandwidth 6-to-1, and it's okay.
Are you saying your drives aren't on a SAS bus?
I'm saying they're not. They're on a point-to-point interconnect where every single drive has a full 6 gig lane into the
6 gig
CPU.
SAS lane.
Correct.
So, it's
What's the problem?
that's very different, for example, from how Violin architects it, right? I mean, you may build your drives, but you still have a SAS drive on a SAS bus. You may not go through a SAS expander, but you're using off-the-shelf chips, off-the-shelf ASICs to put this thing together.
That's correct. We are using off-the-shelf chips, off-the-shelf ASICs. I don't believe the differentiation is actually in the module. I think the differentiation is in the system architecture. And I think our performance numbers on a system level speak for themselves. I mean, we're getting 8 gigabytes a second, 800,000 IOPS out of a box. I think, where your box is, David, if I saw the quotes right per node was around 1/16 of that. So I think there is a definite difference between
Technology, not products, gentlemen.
So
I'm speaking about technology because I'm speaking about what a point-to-point SaaS architecture does versus a shared expander-based SaaS architecture. PCIe architecture is a totally different one. Happy to have it. The reality is that PCIe, I'd love to use it today. It's not hot swappable. It's not quite there yet. When it is, I think it'll get there. I think I'm okay with that. But next panel maybe.
So,
Which will be on.
so obviously,
20 seconds.
okay. So fundamentally, I think that you need to start from the flash chips, because if you start from commodity SSDs, each one of those was designed to operate independently. They don't work. 64 SSDs. It's not like they're coordinating their efforts. And if you've ever done RAID across spinning disks where one of them is slow and see performance collapse, when you do it with SSDs, it's like, think of all the SSDs having fast, slow, fast, slow.
Thank you. David, final comment?
So I would agree that system architecture is important. The question is silicone architecture important? And I would argue that building your own silicone, building your own controller chips, building your own bus interconnects is really only important for the tiniest fraction of applications where latency is that important. The rest of the storage industry, everybody, including the big guys, is moving to industry standard, off-the-shelf hardware from standard vendors, just like the networking industry is as well. And it's all being differentiated based on the software and management that you're putting on top and what you do with those raw commodity components. That is the way the industry is going, except for a tiny, tiny fraction of extremely performance-sensitive workloads.
Thank you very much, gentlemen.